Well, greetings once again, everybody. Welcome to Trigonometry for Students and Surveyors. We're at lesson 21 now. It's been a little while since I've done this. Summer came and planted gardens and getting ready to do some kayaking and camping. And so I've been away from my whiteboard for a while, so I'm probably a little rusty, so bear with me. As promised, we're going to get out of the angles. We start out with right triangles, oblique triangles, inversing coordinates, so on and so forth, angles, that kind of stuff. So we're going to go into horizontal curves right now. Horizontal curves is an essential part of road building. I guess I'm referring to civil engineering. The simple horizontal curve is part of every curve on just about every street. Now what I'm going to leave out on this one, we're only going to deal with the internal curve, the curve to start with. What you're not seeing here, these two radius lines, there would be tangent roads, and then there'd be a point of intersection, a PI up here. We're going to leave all that for the next lesson, and so we'll just concentrate on curves for now. So let's go with, let's just start out with the curve is, first of all, what you want to look at here is, this is a full curve, a full circle is 360 degrees, 90, 180, 270, and 360. So a full circle is 100% of the circle. And we want to deal with, we're always dealing with percentages, so there we go, 100%. So over here, 90 degrees would be 25%, 180 degrees would be 50%, 270 degrees would be 75%, 360 degrees is 100% of the circle. Okay, so we got that. Now we want to look at the radius. A lot of things are done by radius. Normally, when you're doing curves on plans, you're usually giving curve length, or you're given radius, angle. You might be getting curve length, the chord. So these are the parts of a curve. And this is the radius. And so to find a radius is half the circle, half the diameter. Twice that is the diameter. You take the diameter times pi, which is 3.1416, and in your calculator, you're better to just to recall to bring it out, because it carries all the extra decimals for you. And then, so in this case, we have a 60-foot radius, and that gives us a 376.9911 circumference. Now, I'm just making a symbol for feet. You can call it centimeters, meters, whatever you want to call it, miles, kilometers, just whatever you use, just make sure that it's all stays the same. Okay, so what we have here, what we're trying to solve on here is we're given the radius, and the angle, then we're going to solve a bunch of stuff. So the radius is 60 feet, we got that. Now our central angle, which is, we call it in surveying, at least up here in the Northwest, we call that the delta angle. And the deltas are sometimes they're divided up, like on a curve return, half delta, 1/4 delta, 3/4 delta. You'll also have a point where maybe the wheelchair ramp comes in, so you'll have deltas in, you'll have angles between those major ones. And of course, if you're dealing with grade, you'll have grade breaks at certain ones. Depends on if you have a catch basin over here or something like that. You'll have everything flowing to it. But that's way beyond what we're doing here. So we're given 60-foot radius and a 52-degree angle. That's our central angle. Now, what we want to do is, what do we have here? Okay. So we're first saying, let's solve the curve length. There we go. So what is the length around this curve? This is where the percentage comes in. How we figure that out is 52 degrees is what percent of 360? It's 0.1444%. So you take that 0.144%, and of course you might want to, I have that stored as 2. You multiply that times the circumference, and our curve length is 54, 45, 43. And I went ahead and I stored that as C. Now I've showed you, I have an HP35S. You can also store that in your free 42, or if you have another type of calculator, you really should be familiar with how to store and recall numbers, because it's every time you make a calculation and store it, it stores it stores away out, stores all the decimals way out. For instance, there we go. You can hit show. I don't know if this is showing up very good, but it's showing decimals about 12 or 13 decimals to the right. Doesn't matter a whole lot. If you just carry it out to 4 decimals, you're fine. The reason I like to what's called fix your decimals, fix at 4, is because then you have your decimals set up for degrees, minutes, and seconds. And if you have it set up at 4, the last decimal is 10,000. So you have tenths, hundreds, thousands, 10,000s. That's plenty accurate for anything in surveying or civil engineering or what we're doing. So there's your curve length. We have that solved. Again, how we did that is we have 52 degrees. 52 degrees divided by 360 degrees gives 0.1444. That times circumference now it gave us the curve length. And the circumference is, again, radius times 2 times pi. So now we have that. So now what's another thing that we want to look at is chord length is the distance between this point and this point. Now this point I told you earlier is where the road tangent. A road might have a straight section coming in here. That's the tangent. And then it hits this point where the curve starts. That's called the PC, the point of curve. Curves around and it hits this one, then there's another tangent coming out. Or it could be a reverse curve and go immediately into another curve the other way. Or it could go into a compound curve and curve even tighter or curve looser. But we're just going to assume for now, and then for our next drawing that we're going to do, our next lesson, that we have a tangent coming in and a tangent going out. So this is the PC, the point of curve. This is the PT, the point of tangency or tangent. Any point along here on the curve, we just call those POCs, point on curve. This would be the MPOC, midpoint on curve. Like I say, 1/4 delta, 3/4 delta, 1/2 delta. So now we want the chord length. Back in the day when they laid out railroads and spiral curves like that, they didn't have the ability to enter in a radius point and just inverse on your data collector and figure out where you're at on that curve. They used chords, and they did what they call they flop the angle as deflection angle. That's called a deflection angle, and turn. So they would use chords to do that. People don't do that anymore. They still teach it, and it's still part of the test. So, but anyways, it's good to know chord. So the chord is, the full chord goes across the whole thing, and you notice that this is not a right triangle. So if you split that angle in two, 52 degrees, now you have 2 right triangles. And I put my little square symbols there. That square means it's a 90-degree corner. So half of 52 degrees is 26 degrees. So now we have 2 26-degree angles. And let's see, we have our curve length. And we have, okay, so we have a 26-degree angle, and we have our radius is out here. So when we went back, our very first lessons, 1, 2, 3, 4, we did a lot of right triangles. So you'll notice that the opposite over the hypotenuse, that's the sine. So we're given the angle, and we're given the hypotenuse. So remember, on a right triangle, you only need 2 things. You need an angle and a distance, or 2 distances. Okay, so we only have this one distance. So we're going to go with the sine of this angle, 26 degrees, 26 sine 0.4384, and we're going to go 60 times, and it's 26,3023. So that's your chord length. That's the opposite of this. This is your vertex of the angle. Again, if you go back to those earlier lessons, this is the angle we're referring to. We've split 52 degrees in half, so we have 2 right triangles. So now we have the opposite. The sine is the opposite over the hypotenuse. We knew what the hypotenuse was, so then we multiplied that. 26,3023. If we double that, then we get our full chord length. 26,3023 times 2 is 52,6045. So now we have the full chord length. So that's how you do that. Now we'll go back to another lesson after we got through most of the right triangles. We did some oblique triangles. And over here we have the law of cosines. That's another way. If you have the angle and the distances. Now, and when we did the law of cosines, our distances were different. They don't have to be the same. You can solve a non-right triangle, an oblique triangle this way, but the fact that these are both 60, the radiuses are both 60, kind of makes it a little bit easier. So the law of cosines is a squared plus b squared minus 2 times a times b times the cosine of the angle. The angle's 52. And so 60 squared plus 60 squared equals 7,200. Now, if you're running a calculator like this, you can just run the whole formula out and solve it at the end. It's good. The free 42 for the iPhone and the other phones, they do the same thing. A little bit different, but they do the same thing. Then you want to go a squared plus b squared minus 2. So I enter 2 times 60 equals 120 times 60 equals 7,200 times the cosine of the angle. And that gives you 4432.76. Now you're minusing that a squared plus b squared. That gives 2767.34. 2767, 2374. Now you want the square root of that, and that's going to give you 526045. That is your chord length, and that matches these two half triangles, these two right angle triangles. So there we've taken the radius. So far we've taken the radius and the angle, and we've solved both of these halves. We've solved the chord and we've solved the curve length. Okay, now there's another one here. There's a mid-ordinate. I'll go ahead and give you that one too. Well, we need to find the mid-ordinate is this distance between the apex of the curve, that's the center of the curve, and the center of the chord. That's the mid-ordinate distance right in there. So how do you get that? Well, now we need to solve this length of the triangle right here. We need to solve that. So that could be an adjacent. There's a couple ways to do that. So we'll keep it as a right triangle. We'll go 26 degrees. And then we'll take the, we could either go cosine. Let's go 26 cosine. And now we'll go 60 times 5392.76. So now this is the adjacent and the opposite, but we use the adjacent and the hypotenuse. That's the cosine. It would also work this way as well if we use the adjacent and the opposite. That's called tangent. Opposite over the adjacent is a tangent. That would work as well. That would give us the same answer. Okay, so we have that distance now. That's the distance from the vertex to this point on the mid-ordinate line. And now we also know we have the radius here. So we subtract 60, the radius, from that. So let's just do that. 60, enter, 53.9276 minus gives us 6.0724. 6.0724 is our mid-ordinate distance between this, that's right here. So while we're in this area, we're going to be putting a road in here, and there's going to be another distance here between here and the PI, and that's going to be our external distance, and we'll figure that out too. Pretty easy to figure that one out as well. Not too hard at all. So we're given that. So I think we have chord length, sine. Let's go down here, solve. Okay, you don't always get the angle and the radius. Sometimes you get other pieces of information and you have to fill them in. So of course, like all math, there's ways to reverse it and rework it. So this one says solve the angle given the curve length and the radius. Okay, so use the radius to find the circumference. Okay, so we're given the radius, so let's go with the radius. Radius is 60, and so 120, and then we have pi, so we have our circumference, And so we have our, and we already have our curve length. We've solved that. So we just take our curve length divided by the circumference. That's 0.1444. We come up with that again there. And you multiply that times 360 degree circle, and we get 52 degrees. We're back here now. Now we've solved the angle from the curve length and the radius. So, and so on and so forth. That's how that carries on. The next one is solve the radius and the angle given the circumference and the curve length. All right, let's make sure I'll get confused here. I know I will. Circumference divided by pi is going to give you, okay, we want the radius. Solve the radius, that's okay. Let's go with circumference. We have that 376,911 divided by pi. You divide that by, 120. That's going to give you 120. Divide the 120 by 2. It's going to give you the 60-foot radius. So that part's done. That was pretty simple. And then B was solve the radius and the angle. And then again, curve length divided by the circumference equals that. So we're kind of back to that same problem we did up there. Okay, now let's do number 4 right here. So solve the radius given the chord and the angle. Okay, well our chord is 526045. Now we want a right triangle here. We want to work with that. So we're going to split that in 2. Divided by 2, 26,3023, that's 1/2 the chord. So now we want that angle. What we're trying to do is break down this into a right triangle and figure out what this radius is. So we want the sine, the opposite over the hypotenuse. So we want the sine of 26 degrees equals 0.4384. Now what I like to do is hit 1x, and that inverses it into 2.281, and then multiply that times 26,3023, and that gives us 60. If you don't like to hit the 1x, you put your opposite distance in first, 26,3023, the sine, and then divide it by 26 degrees sine. You divide it instead of multiply it, and then you'll end up with 60-foot radius. So that's how, once you get that, then I think we pretty much solved this one here, made it kind of simple, pretty much simple. Then we're going to superimpose this or get another similar one, and we'll put that in for the next lesson. We'll add the tangents, the pi. It'll be quite a bit more to it, but this is why you need to get this down first. Get that. And so if you need to take a screenshot, I'll get out of the way. Just remember to like and subscribe to Trigonometry for Students and Surveyors, and pass it around, and it's for students too. I think the reason like I said before in my earlier lessons, for a student it's better to have some practical reason, practical application of trigonometry rather than just abstract. Helps you really learn it and understand why we do it. Okay, so that's all. So thank you.